So this is the beginning of our normal distributions. There are 4 sections, and this video has the first 2 sections. So the introduction to normal distributions is the first coverage here. So this is the beginning of our continuous random variable. We've covered discrete with probability distribution and binomial. So just a quick refresher on what continuous means for our data set. It means we have an infinite number of possible values that can be represented by an interval on the number line. Most importantly is these are not just whole numbers, these are going to be decimal values in between. So we're not just counting 0, 1, 2, 3. It's all the little spaces in between as well. So with continuous, we can't put these kinds of things into a chart. So we are going to find very specific probabilities for certain situations, but we won't be filling in a chart of values for this. So a couple slides here to just describe our normal distribution, all of our properties for it. This is our continuous distribution that we are going to cover. It is the most important one. That's why we spend a little bit more time, 4 sections worth on this. And the big thing you're going to get used to seeing on every problem is this normal curve. So it is nice and bell-shaped. It is symmetric. We're going to sketch it quite a few times. And in fact, on every problem we do, we'll make a quick little sketch of it. So there's 4 different properties here on this slide. First one is because of the shape of it, we have our mean, median, and mode that are all equal in the middle. That's what's giving us that bell shape and symmetric look. All of the area underneath the curve is going to add up to 1, which is the same thing as all of our probabilities add up to 1. So when we see the word area, you can also think to yourself probability. So probability is the same thing as P of X. You'll see that noted a couple times here. Area and probability are interchangeable. Also, when you are making this sketch or you see it on a computer, it's technically still going. This doesn't stop. These are little arrows on the end down here that just keep on going in either direction. It never technically touches that line. It just keeps going farther out on either end. So sometimes you will see us put an infinity and a negative infinity on the end, just as a reminder that it keeps on going. Now, one of the other properties that comes up is what's called inflection points. And that's just the visual marking of where our standard deviation measures out. So when we have our mean in the middle, going out to the next bar, as we sometimes call it, this right here, this is 1 standard deviation out. But when we are making our sketches, or really when we see it on a computer, this point right here, that 1 standard deviation out on either side, that is called the inflection point. Because if you know a little bit from physics about concave and convex, it's where our graph changes from being a curve facing downward to a curve facing upward. That's the inflection point right there in the middle. So that's what's happening on either side. Now, when we are making our sketches, you don't have to be super specific and finding that point. But in this first section of homework, you're going to have a couple where you are guesstimating where your standard deviation is, and that's what we're going to be looking for. We're going to look for that inflection point. And if you zoom in on that spot, it's a little section that looks almost linear. It's almost like a little straight line in there. That's where we're looking for. Now, just to see a couple of these side by side, all of our data sets are going to be a little bit different with different means and different standard deviations. So visually, if you put them side by side, they will look a little different. So the first thing is the mean is giving you the location of where it is on the number line. So as you notice on these graphs, the first 2 have the same dotted line at 3.5. And then the third graph over here is at 1.5. So you'll notice the hump of the center of your graph has moved to the left. So the center of your hump is always going to be your mean. Your standard deviation is going to talk about that spread or variation of your data set. So the larger your standard deviation, the wider your graph is going to look. And the smaller your standard deviation, the more narrow your graph will look. So keep in mind, the area under the curve always has to equal 1. So kind of imagine you're playing with Play-Doh. If you have it more spread out, it's going to be flatter and wider. But if you want to like make it taller, it's going to have to get narrow on the sides in order to get that height. It's not like we are adding or subtracting any Play-Doh. So it's still that same total area underneath, which is why the height of your graph looks like it's changing. So it depends on how spread out your data is. So we typically think of it as wider or narrow, but if you have them side by side, you might also notice a height difference between them. So here's our first just beginning problem. Looking at these two curves, A and B, which one has a greater mean? So if we're talking about the mean, you're talking about the center of the hump. So find the center of both of those humps, and then you're comparing the numbers on the number line. So between 12 and 15, 15 is bigger, and it's coming from curve A. So curve A has a greater mean here. Now, if we're using those same two graphs and we want to know which one has a greater standard deviation, remember we're looking for the wideness or the narrowness. And because we want the greater one, we're basically asking you for which one is wider. Which one is wider? And with that, it's going to be shorter. So in this case, it's curve B. So here's another example. It says the scaled test scores for New York State grade 4 Common Core mathematics tests are normally distributed. The normal curve shown below represents this distribution. What is our mean test score? So again, the mean is the middle of your hump. So find the middle and kind of drop that line down. Just ballpark it. Each one of these tick marks is about 10. So let's see, that's 290, then 300, 310, 320. So probably 310, approximately 310 for mean. Now, when you have a problem like this in the homework, it will expect a range of answers. So don't worry about like pulling out a ruler and making it exact, but try to get as close as you can. The second part of this question says estimate the standard deviation. So that's where this inflection point thing's coming in. So you can do it either on the left side of the curve or the right, doesn't matter. But you're looking for kind of like this little section here where it looks like the line is getting pretty straight, pretty linear. And I'm just going to pick right in the middle of there and drop it down to one of my tick marks. Now, standard deviation is the distance between these two. So if this is 330 tick marked, and this is 340, 350. So I'm taking 350 minus my mean, 310, to find the distance between them. That's my standard deviation. That's where most people get tricked up on this one, is we want the distance between that inflection point and your mean. That's your standard deviation, is that distance. So just to recap, you've seen your z-score formula before. That's going to allow you to go from any data set you have to a standardized normal curve. So that way we can compare different data sets to each other. We can use empirical rule with this. We can do a little bit more with this. So a standard normal distribution looks the same as what we've just been doing, except for now we have a mean of 0 and we have a standard deviation of 1. So that's what's making this a standardized curve. So you'll notice across the bottom of a standard curve, you have 0 in the middle, and you typically go out to a positive 3 standard deviations to the right and 3 out to the left down to a negative 3. So when we're making our sketches, this is the one we are working with. And in order to be able to use that graph, that's where your z-score formula comes in. you can plug in any x value with the mean and standard deviation from that data set and turn it into a z, which can then go on our z curve or our normal curve. And same information, just again, the reminder, the total area underneath your curve is 1. That's the same thing as saying all of your probabilities add up to 1. Now, in order to find the areas under a standard normal curve, we're going to need your calculator, and we're going to use a function in your calculator called NormalCDF. So I'm going to write that on here, NormalCDF. Keep in mind there's 2 in your calculator. One has a PDF and one has a CDF. We want the C, and think of it as this is continuous. I want that continuous function here. So if you have a problem where you want to find the area to the left of the Z, so say something like this, we've got 1.23 is our Z score, and I want to find all of this blue space to the left. We're going to go in your calculator to second vars. These are the 2 buttons you hit. And then you will see on that list, NormalCDF. What you will find is that it will prompt you for your lower, your upper, your mean, and your standard deviation. It's going to ask you for 4 things. Because we are using Z's, and we have our Z-score formula, we are always going to keep a 0 and a 1 in for your mean and your standard deviation. 0 and 1. What you're going to change each time is your lower and your upper based on the area that you want to find. So think of it as lower as being your left side, and your upper is your right side. So looking at this little example on here, my shading is coming from way down here on the left. Remember, that's negative infinity. It keeps on going. We don't actually have an infinity symbol on our calculator, so we just need a really, really big number for down there. And because we're talking about Z's, Z's are always going to be between like that -3 to +3 area. We're going to plug in a -100. Now that might not sound like a really big number, but that's 100 standard deviations out to the left. That's a lot. And in fact, if you add a few more zeros onto that, you're not going to notice a change in the answers that we are going to get. So that's a big enough number that we're going to get our correct answers every time. But if we needed more decimals, we might add more zeros. But we're going to do -100 through all of this course. So that's our lower. If we're ever talking about negative infinity, use -100. On the right, the upper, all of this shading goes up to this number right here, 1.23. That's what we would put in as our upper. So this is describing between your lower and your upper all of the shaded space we want to find. So if we want to find all the area between those two, we click paste underneath those 4 options to fill in. And then I'm going to get you in a habit of rounding it off to 4 decimals. We get 0.8907. So just in case you want to go ahead and check and make sure you get the right number out of that. Now, if we wanted the other side, we want to find the area to the right of Z. So over here, same thing. We're going to go second vars. We're going to select NormalCDF. For our lower this time, our left side, we are going to type in the 1.23. Remember, this is our left side. And this time for the upper, which is the right, Because we are going all the way to positive infinity, we're going to use a positive 100. Mean and standard deviation are always 0 and 1 when we're using z's. So second vars, click on NormalCDF, type in 1.23 for lower, positive 100 for upper. Mean and standard deviation will always stay the same. And if we round it to 4 decimals, we get 0.1093. And again, on the right-hand side, that positive infinity would equal a positive 100 when we're talking about upper. Now, the last situation that will come up is if you ever want to find the area between two z-squares. So as you can imagine, you have a z on the left and you have a z on the right. That will be your upper and your lower. So NormalCDF, you'll put in your lower as negative 0.75. You'll put in your upper as 1.23. Your mean is 0. Your standard deviation is 1. And in between the two of them, you will find .6640. Now here's one of our first examples. Find the cumulative area that corresponds to a z-score of 1.15. Now the first thing you might think to yourself is it doesn't really say, do I want to the left, to the right, in between? It just gives me a z-score. If it doesn't say, then it is automatically to the left. We want everything to the left of that spot. So I always find it helpful to make a quick little sketch. So this is my little normal curve. My z-score is positive, so that's somewhere to the right of my hump. Keep in mind your z-score curve, 0's in the middle. And then it's positive numbers to the right, negative numbers to the left. And again, because it didn't state, it's automatically to the left. So I can go to second vars, click on NormalCDF. NormalCDF. For lower bound, I'm going to type in negative 100 to represent that negative infinity. For upper, I'm going to put in the 1.15, 0 for mean, 1 for standard deviation. And when you click paste, it brings it back to the main screen in this order that I've just written it. It is always in the order lower, upper, mean, and then standard deviation. So this is exactly what I'd be looking for if I want to see your work on something. Showing me what function you use, all of those numbers you plug in, and then the answer you get out from it. So for this one, we would get 0.8749. Let's try another one. Find the cumulative area that corresponds to a z-score of negative 0.24. Same thing, this one didn't state it. So if it doesn't state it, it's automatically to the left. So make a quick sketch. Since our z-score is negative, our line would be to the left of our hump. You'll notice that I don't make a full number scale underneath. You can if you want to, you do not have to. These are truly quick little sketches just so I can see that you know where you're looking for that area. So then we can go to second vars, click on NormalCDF. For lower, again, it's negative 100. Upper is negative 0.24. Mean is standard deviation are 0 and 1. We click enter on paste to bring it back to the main screen where you see all those numbers in that same order. And then when you click enter for your answer, we get 0.4052. So that first section is covering all of our properties and a quick little intro into using that calculator to find the areas. Keep in mind, area is the same thing as probability. So in this next section, we are finding probabilities. So here's kind of an example of what you're going to be provided with here. So a problem will present like this. It'll say something to the effect of, you have a random variable, x, it's normally distributed, and we want to find the probability of that x in some interval by calculating that area under the curve. So whether they give you a sketch or not, they will need to tell you your mean and standard deviation, and they will need to tell you what they're asking you to find. Sometimes they'll give it to you as a P of, like this one right here, x less than 600. Or they might say, in the situation, truly x less than 600 in the wording of the problem. I always recommend you find all the information, you make the sketch. We're going to have to switch all of this into a z-score, and then we use our calculator with NormalCDF. So let's try it out. Here's our first example. A national study found that college students with jobs worked an average of 22 hours per week. The standard deviation is 9 hours. A college student with a job is selected at random. Find the probability that the student works for less than 4 hours per week. Assume that the lengths of time college students work are normally distributed and are represented by the variable x. So you have a mean, a standard deviation. Always find that sentence that says find the probability of, and notice here's your inequality right there with the number. So we want to find less than 4. And the conditions that are helping you figure out what to do and when is the fact that this says it is normally distributed. That's why we can do NormalCDF and we can find a z-score. So just to give us a little bit more space, again, our mean was 22, standard deviation was 9, and we are finding the probability that x is less than 4. So if we wanted to make a quick little sketch, before we start putting all of our numbers on there, we want to find that z-score. X minus mean over standard deviation. 4 minus 22 over 9 gives us a -2. So because it's a negative, it's going to be to the left of our hump. Because it is less than, we want to the left of that line. So this is -2 is where the line is at. That less than is telling us to shade to the left. Now, because we have the sketch, it makes it a little bit easier then when we go to do NormalCDF. So second vars, click again on NormalCDF. Our lower bound is -100. And again, negative infinity, same thing as using -100 in our calculator. -2 for upper, 0, and 1 for mean and standard deviation because we are using z-scores. So as soon as you use that z-score formula and switched all of our numbers into that -2, those back two numbers need to be 0 and 1. So NormalCDF, again, everything less than -2, we get 0.0228. Now, with our homework in my stat lab, oftentimes they just want that final answer I boxed in. But keep in mind, for showing work for a problem like this on a worksheet or on a quiz or on a test, you will want to show all of these steps. Being able to make the sketch, changing your values into a z-score, what you plugged in with the calculator, and that final answer. Here's another one. A survey indicates for each trip to the supermarket, a shopper spends an average of 43 minutes with a standard deviation of 12 minutes in the store. The lengths of time spent in the store are normally distributed and are represented by the variable x. A shopper enters the store. Find the probability that the shopper will be in the store for each interval of time listed below. And then part B, when 200 shoppers enter the store, how many shoppers would you expect to be in the store for each interval of time listed below? So part A is just like what we were doing. We're just going to do it twice since we have two different situations here. But I do want to just quickly, briefly talk about this 200 shoppers. That is your sample size. N is 200. So what we're going to do in a minute is do N times the P times your probability you found to figure out the X, how many people are in that store. So that formula has actually come up before when you were doing X divided by N to find a probability and the probability distribution. But now we've just kind of rearranged it a little bit. So in a second, we're going to take our N times each probability for that piece. So let's try this first one. It says between 22 and 52 minutes. So again, our mean was 43. Our standard deviation was 12. We want to find the probability of X being between 22 and 52. And then later we're going to use that 200 for N. So the first thing we need to do is switch this into a z-score. X minus mu over standard deviation. Now what you'll notice very quickly when you go to plug in, you have two different X's here. So that actually means you have to do this twice. Two different z-score formulas. We're going to have to switch them both into a z. So 22 minus 43 over 12 for the first one, and we get negative 1.75. And then we can plug in 52 for X on the second one here. We get positive 0.75. So we have two different z's. So if we wanted to make a quick sketch, negative z means to the left of the hump, positive z means to the right of the hump. And we want to find that area in the middle. So when it comes to our calculator, NormalCDF, our lower is negative 1.75. Our upper is positive 0.75. And our mean and standard deviation are both 0 and 1. We find that area under the curve then to be 0.7333. And this is our answer for part A. Part B says when we have a sample size of 200, how many people do you have in the store? So N times P, 200 times that 0.7333, the one you just found, and you get 146.6627. Now they do want to know the count of total people in the building. So you're actually going to round down on these, regardless of decimal, to the whole number underneath. So 146, that's how many total people are fully into the building, if you want to think of it that way. This 0.6 is the majority of a person, but they're not quite fully into the building yet. So you are going to round down when you're finding this X value. Now we found the one that was between. We had another one we needed to find where it was greater than 37. So if we write out what we had again, we had our mean 43, standard deviation of 12. We're finding the probability being greater than 37 this time. So we can start with our z-score formula. X is 37. We get negative 0.5. We can make a sketch of our curve. Since our z is negative, our line should be to the left of the hump. And since it is greater than symbol, we want to the right of that. So normal CDF, our lower bound is negative 0.5. Our upper bound is 100, which is taking the place for that positive infinity. 0 and 1 for mean and standard deviation. And then we round off to 4 decimal places. This is our answer for part A, 0.6915. And then again, if we have 200 people in the building, N times P, 200 times that 0.6915 we just found, we get 138 and change, which we want to round down to 138. That's how many total people are in the building.